pull up our notes from yesterday. Okay, so I believe this is where we left off yesterday in our packet. As we continue to move through here. We've got our weak bases that we had started to talk about. Here we go. Okay. So they had wanted us to write the Ka expression here for acetic acid. I'm praying that this pen still works today. Yes, good. Okay. It's just not changing colors for me for some reason. Now, Ka equals. Our Ka expression then is going to be our products here over our reactants, but we don't put water in the equilibrium expression. Pure water is left out, okay? And I did not underline that. I just kind of, there we go. Meant to underline it, didn't work so well. Okay, so pure water is left out of the equilibrium expression. So when we're writing our equilibrium expression, it's going to be Ka equals, we're going to have the concentration of our H plus ions, concentration of our acetic acid ions, and that's going to be over concentration of our HC2H3O2. Okay, and I don't know how far we're going to get today, but at some point I will show you how to do these for a weak acid. Okay, you got to use those ICE tables that I taught you last chapter, and that'll kind of connect some of the stuff that we did last chapter with some of the stuff that we're doing this chapter. Okay. Yeah.
About yesterday's notes. So, when I was just wondering, do strong acids and bases not equilibrize if they only go one way?
Right. Yeah. Because they are strong acids and bases, they're not going to establish an equilibrium. So there won't be, you know, like here, we would have it going this direction and we would come back having it go this direction. All right. When you're dealing with a strong acid or a strong base, it's all in one direction. So because it's all in one direction, everything is over here. You end up with that. There's nothing swinging back the other way. So that's why the strong acid and strong base, we don't do the Ka, Kb expressions for them. Okay. All right. But we do have the Ka and Kb for weak acids and bases, and that's what we were talking about today. So with weak bases, how they work is if we've got like our ammonia ion here, which is NH4 or NH3, what will happen is a molecule of water will come by, and this lone pair of electrons on this nitrogen here will end up pulling that hydrogen away and attaching it. It's going to make ammonium ion, gives it a positive charge. And then it leaves behind, from this water, it leaves behind the OH ion. And so your OH ion here is what, you know, we calculate that OH ion to determine the strength of the base. And that happens with a lot of these different molecules: methylamine, dimethylamine, trimethylamine, ethylamine, pyrimidine. You might recognize this guy from like biology class if you did any kind of biology stuff. Pyrimidine is in there. I believe it is one of your amino acids, but don't quote me on that because it's been a very, very long time. But these end up pulling that OH ion or the H ion from the water. So that ends up attaching here, and then that leaves behind the OH, which is where your base values come from. Okay, so the Kb expression is the same way. With the Kb expression, how do you know that you have a Kb expression? You're going to have hydroxide as one of the products here. So it's pretty easy to recognize when you need to be using Ka and when you need to be using Kb. All right, so Ka, you're always going to have hydrogen up here, an H plus. Remember that we can use H3O plus and H plus. We use those interchangeably. Okay, but at any rate, when you have a Ka expression, you're always going to have that hydrogen ion up there in that expression. So you're going to be looking for that. Okay, if you have that hydrogen ion in there, then you're in the land of Ka. If you have the hydroxide ion in there, then you're in the land of Kb. Okay, so this would give you your Kb. All right, so here they want us to write the Kb expression for ammonia. So first of all, we need to come up with the equation for what happens when we put ammonia in water. Please work, please work, please. There we go. So NH3 plus water is going to give me, and how do I know that it's going to be an arrow like this?
Weak.
It's weak. How do I know it's weak? Because it's not strong.
It's not one of the alkaline.
Mm-hmm. Yeah, it's not one of the OH, the KOH, NaOH, LiOH, right? It's not part of those big six. Okay. All right. So this is my base. This is going to act as an acid. Remember, water is amphoteric, which means sometimes it acts like an acid, sometimes it acts like a base. Right now, it's going to act like an acid, and it's going to give one of those H's to the ammonia, to make ammonium ion, and then we're going to leave behind the OH minus. So when we write the Kb expression for this, let me do it good. I can get a skinnier font then. When I write the Kb expression for this, then my NH4 plus, I'm going to have OH minus on the top. I know that I'm doing Kb then because I had OH minus on the top. And that's going to be over top of NH3 on the bottom. I do not put water in my equilibrium expressions. Water is not present in those. Okay, so again, notice that the Ka and Kb expressions look very similar. Difference is that a base produces hydroxide ions. Acid is going to produce hydronium ions. Hydronium ions are hydroxide are OH minus. Hydronium is H3O plus, sometimes referred to as just H plus. Okay. So, like I said, we just leave out the expression with water in it. We don't do that. If you did the homework last night, you understand that what this H3O plus looks like is essentially you've got your water molecule. The lady calls it Mickey Mouse, okay? And it's going to be Mickey Mouse with a chin with this hydronium. So if we look at that in terms of what that actually looks like, if we do a Lewis structure for this, we have our water. Okay, water has those two lone pairs of electrons. We have a hydrogen here with a shared electron from the hydrogen, so that electron came from the hydrogen. Then we have another hydrogen here with the electron from that. Then we have an H plus that's come along. Does that H plus have an electron? No, because it's H plus. So it's lost its electron and it gloms on right here. So that's what your hydronium ion ends up looking like. Okay?
So it has a lone pair of the oxygen.
And it's a plus charge, yep. And that's why your hydronium looks like that. But a lot of times we just refer to it as that. Okay? So here they want us to use this table, the 14.2, to arrange the following species according to their base strength. Now, look at this chart. Control C. And I will try to do a Control V here. Do you think it's going to be friendly to me? I don't know. We'll see. Here it is. Good. I can. Good. Oops. Be nice. Get along. Now, they're asking me to look at relative base strength here. Okay? Base strength. Base means we're in the land of what?
KB.
KB. But this gives us Ka. Okay? So we could convert to Ka, or Kb, I mean. We have a conversion for that. I will teach you that. It's coming. Or we could just look at this and realize that if we have a strong base, then we have a weak acid. And if we have a strong acid, we have a weak base. So if we identify these from strongest acid to weakest acid by using the Ka value, then that would order it from the weakest base to the strongest acid, or I'm sorry, the weakest base to the strongest base then, right? Does that make sense? Okay, so let's look here. If I add H's to these, does anything pop out to you as significant? Which one?
There's just one H.
Oh, there's just one H. But anything among these four things that I wrote here, anything there like scream to you something significant? Like one of those things should be screaming at you. HF is weak. Yep, you're right. It's in this chart. Why is this one screaming at me? What is significant about HCl?
It's strong.
Yes. This is a strong acid. So if this is a strong acid, that means that this must be a weak base. Okay. So if we're ordering this from weakest to strongest, we know that that guy is going to come first in our list. From weakest base to strongest base. We want strongest over here. Okay. Now, water is, what do we know about water? It's neutral, right? Water's right smack in the middle. It's right smack in the middle of all of these. The rest of these are going to be a little bit stronger bases. So water is going to come next in our list because it's neutral. And then we've got to order the rest of these. So we've got 3 left here. We've got rid of this one and this one so far. So now we've got to figure these out. Okay. So if I look at my values over here, I see that HCN is right here. That's my HCN. It's not going to let me write on it, but you see it right there. Okay, it is 6.2 times 10 to the negative 10, since it won't let me write on it. HNO2 is 4 times 10 to the negative 4. And HF is over here. It is 7.2 times 10 to the negative 4. Okay, so we are going to order these in order of smallest or biggest to smallest. Okay, this is obviously the smallest of these. We can look at the expression times 10 to the. So we know that CN is going to be our strongest base because our weakest acid is our strongest base. Does that make sense? Okay, so I have to now figure out where I'm going to go in order with these two. Okay, so which number is smaller here? 7.2 times 10 to the negative 4 or 4 times 10 to the negative 4?
No.
Which did I ask? Which is smaller or which is bigger? I don't remember.
I keep thinking of that.
which one would come after H2O? Well, let's take these and take them out of scientific notation and see which number is bigger and smaller. So
wait,
1, 2, 3, 4. Which number?
HNO2.
Okay. So this is going to be HF here, or F, I guess it would be F minus. We're talking about the base. And then we would have our NO2 here. And that should be our answer. Now we can go back and cheat and see what it says.
So if we're trying to do the opposite, then we're basically listing them in strongest to weakest acid.
Yeah. So this was the strongest acid to the weakest acid, which would make this the weakest base to the strongest base.
So how do we know that water comes second?
Because it's not a strong acid, okay? And it's not, it's stronger. It's K. Not sure. I just know that your strong acids go over here, your weak acids get ordered here, and your water is somewhere in between. Other than that, I'm going to have to think about it, Eric. I'm sorry.
Sorry.
All right, so moving on. You remember when I told you that water doesn't conduct electricity?
What is this?
Huh?
I mean, distilled.
Yeah, distilled water. Remember when I told you that? Yeah, I lied. Again, I lied. I know. There's just so many times that I lied to you last year. Yeah. Okay. It has a small, minute amount of electricity that it does conduct. Okay. But we're talking a really stupidly small amount of current. Okay. Like a stupid amount. Small. But technically, it does. Okay. So, about, I don't know, 2 out of every billion with a B, water molecules are ionized. So that's why I mean it's a stupid small number. Okay. But it's amphoteric and it does disassociate to a very slight extent. Again, about 2 in a billion ionize. So this is the process that it goes through. Okay. So we look at pure water. We can have an equilibrium expression here. We call that the autoionization constant for water. We call that Kw. Okay. So we have now been in the land of Kc, Kp, Ka, Kb, and now I'm adding Kw. Lots of Ks, huh?
Yeah.
Mm-hmm.
Wasn't that?
Oh, and we had KSP too. I forgot about that one.
Wasn't KW on the progress check at one point, I believe?
Well, I believe we talked about KW back when we did acids and bases, and it is on this sheet. So you've seen it around, okay? And we'll talk about KW here in a couple of minutes. But we've got this slight ionization here, okay? So water, pure water, the concentration of pure water can be considered a constant. This is actually the concentration of pure water. Okay, and you're like, are you serious? Yeah, it's like that crazy high. Okay, now how do I know that? Well, I know that the density of water is 1 gram per milliliter, right? Okay. And let's just say that I have 1 liter of water, just to make life easier, because that makes our molarity easy, right? If we have a liter. Okay. So that would mean that in 1 liter of water, I have how many milliliters? 1,000 milliliters, right? Okay. So if I have 1,000 milliliters, how many grams, since we know the density of water, how many grams would be in a liter of water? 1,000 grams, right? And if I had a liter of water here and I wanted to know how many moles it is, because if I want to figure out molarity, I've got to figure out moles. What do I divide this 1,000 by? Well, I want to get this into moles, so I divide it by...
Oh, it's mole.
Right, so 18 for water. I told you guys last year to memorize that because it makes life easier. So when I do that, that comes out to be 55.6. Okay, that's moles, and that would be in 1 liter. So that's how they get that molarity there. But this is so massive compared to what we're working with for our concentrations for these other things that we just ignore it. Just like back when you were doing that crystal violet reaction, you ignored the sodium hydroxide because it's just such a large magnitude more that it's not going to make a difference. Okay. So our KW, now this is at 25 degrees Celsius. Remember, our K values, our constants, our equilibrium constants are all temperature dependent. Typically, most of the stuff that you will do will be at 25 degrees Celsius. Why do they pick 25 degrees Celsius? Just randomly, like, oh, that sounds like a good number. Why would they pick that number? And not like 100 degrees Celsius or 0 degrees Celsius. Why would they pick this one? Huh? Yeah. It's about room temperature. So this is about the temperature that you would be working in most conditions. Okay. Now, sometimes conditions vary. Okay. And we'll get into that when we get into thermochem and how, like, why batteries don't work this time of year outside. Okay. Or I don't know if you guys have ever like left your Chromebook. If you left your Chromebook outside, okay, in your car when it was these 0 degree days out and you tried to bring that in and get it started and it's one of these ones that you've had since you were a freshman, there's a good chance that the battery was dead on that thing or it just would not function because they have a heat tolerance. Okay, a certain level that they'll work, and we'll talk about more of that when we get into thermochem. Yeah.
Is that the same reason why they tell you not to keep it in the heat too?
Mm-hmm. Yep. Yep. So our KW value here, our KW equals our hydronium concentration, or remember, you can think of this as your H plus, times your hydroxide concentration. This value equals, and we just call it 1. We won't mess with the point, the 0.008. This is 1 times 10 to the negative 14. Your Ka times your Kb at 25 degrees Celsius also equals this. So if you know one of these, you can always calculate the other one. And I actually store this value in my calculator as W so that I don't have to type it in all the time. If you know this value, you can calculate this one because this is a constant at 25 degrees Celsius. So you can, this right here, this KW allows you to like be able to slide easily between all of these different values. Yeah.
So KW is always 1 times 10 to the negative 14?
At 25 degrees Celsius.
That's not a blue sheet.
It is. Yep. That value is on your blue sheet. It is in the first section of your blue sheet here, okay? And it says KW, and it gives you all of this equals this. It says at 25 degrees Celsius, and then it says also right underneath it on the blue sheet, it's underneath, but it says equals these two things. So if you know this, you can get this. If you know this, you can go all the way, you can slide through these things. Okay? Because you can calculate the other ones. All right. So if your OH equals your H, you're in neutral territory. If your OH is greater than H, you're basic. And if your OH is less than H, you're acidic. Now, this question says, if we were working with KW and we're at 60 degrees Celsius now, they want us to tell whether, now that we know that our KW is this, they want to say whether it's an endothermic or exothermic reaction. Don't look at the answers down in the corner. Don't cheat. Put your hand over it and don't look. Cheaters. Le Chatelier. All right, did you figure it out? So look at this right here. Okay, this value is small, is bigger. Let me say it that way. It's bigger than this value. Yes? Everybody agree with that? Okay. So that tells me that when we increased our temperature here, okay, that my products became more favored. So as I increased the heat, it shifted the reaction this way. Does that make sense? Like logical, linear sense. So that means that heat, if heat was added over here, it's going to push it this way. If I had added heat here and it was exothermic, it would have pushed it this way. So if heat is on the left side of my reaction, which is it then? Endothermic. Okay, and hopefully you figure that out by not looking at the bottom. All right, so then at this neutral condition, they want us to calculate our value for our hydronium and our hydroxide concentrations. Okay, so we know that's the answer because we cheated, but we need to know why that's the answer and how they got it. Okay. So this is taking us back to the land of rice or ice tables, depending on how you want to call them. So 2H2O yields my H3O plus my OH minus. Okay, this is my reaction. My ice table goes in here. Okay, so I don't mess around with water. I'm not going to calculate that in, so I'm just getting rid of that side of my equation. Don't need to worry about it, kind of like we did when we did our KSP values. Okay, But over here, I need to work on this. So initially, I was at 0 here. I would add x to both of these, which means at equilibrium, each of these would equal x. Yes? So that means that my kW would equal what? X squared. Okay. We know that kW, they gave us up here what kW was. So x squared is going to equal 1 times 10 to the negative 13. So if I want to calculate x, all I have to do is take the square root of both sides, right? And when I do that, this is what I get for my answer. Yay or nay? All right, going back to pH. You guys, this should be a total review. All right, so when we talked about pH, we talked about hydrogen concentrations or hydronium concentrations. And if you remember correctly, we had the H here. The pH then was equaled negative log of that hydrogen concentration. Do you remember this? We did this first semester, right?
I remember you saying it on the video last week.
Okay. POH is going to equal the negative log of the hydroxide concentration. And if we want pH plus POH is going to equal 14. Now, if we're given pH, you can go 10 to the negative pH, and that's going to give you, that's going to equal your hydronium concentration. 10 to the negative POH will equal your hydroxide concentration. So you can go the other direction with this too. So you can go from, you can calculate pH by going negative log, or you can go 10 to the negative pH and get back to this concentration. Does that make sense? Okay. Let's see. Yeah, we're not going to worry too much about pH with sig figs. Okay, that's just going to get gross and disgusting. All right. So here, I want you to try to figure out, see if you can figure out whether these are basic or, so figure out if you use these, if you can do this, then you can figure out if these are going to, what their pH is going to be. And then from the pH, you can determine if it's going to be acid, base, or neutral. Oh, and do you have your ID? Just kidding.
I was going to start doing that now.
All right. So yeah.
Oh, so is the answer just a positive exponent?
It is if your leading number here is 1. Okay. If your leading number here isn't 1, then no. But whatever this exponent is, it's going to be right in close range with what the pH is going to be. Because, I mean, that's essentially what a log is, right? It's just a magnitude of 10 is what it's telling you. So yeah, if your leading number here is 1.0, then yes, your exponent will be your value. Here, that you would have converted this if you converted that into H concentration and then that over, or you could have found negative log of this and just subtracted from 14. So you can do the negative log of this, it'll give you 5, and if you subtract that from 14, you get 9. Right? What's wrong?
Oh, okay, because I just did just POH equals negative log of the concentration for the first two.
Right, but that would have given your POH, which would have been 5, right?
Yeah.
Did you get 5 for your answer? Yeah. So but that was your POH. So here your POH would have equaled 5.
Okay, so it wants it in pH?
Well, it's asking you if it's neutral, basic, or acidic. So this is going to be basic because its pH is 9. This will be neutral.
Okay, because we always have to get it into pH.
And this would have been acidic. This one, they gave you the H concentration. They didn't give you the OH concentration. So you got to be careful. They're sneaky that way.
Wait, so not the Seaburn?
C, they gave us the H concentration, not the OH concentration. So this, you would just take the negative log of 10, and that's going to equal your pH. This one, you would have needed to take the negative log of 1 times 10 to the negative 7, and then subtract, that would equal your POH, and then you would subtract that from 14 to get your pH.
I'm just confused how you got 0 for C. I got negative 1.
Oh, was it negative 1? So negative log of 10. Yeah, it did come out to be negative 1, but we don't do negatives for pH. 0 is the lowest we go. So. All right, good. Ready to move on? All right. So here we've got calculate the pH and POH for the following solutions at 25 degrees Celsius. Again, don't cheat by looking at the answers yet. Naughty kids, don't do it. Okay. So this is our OH value here. Okay. So if this is our OH concentration, can you figure out POH? I always figure out POH right away and then subtract from 14. Or here, I would figure out the pH and then subtract from 14 to get the POH. Did you get these answers? Anybody need more time? Okay. All right, here we've got human blood. What to drink of blood? pH, human blood, 7.41. We're going to calculate the POH, the H concentration, and the OH concentration for the sample. Remember that to calculate the H concentration from pH, we go 10 to the negative 7.41 0.41, that's going to equal your H concentration. And from there, you should be able to calculate the other stuff. See if you can get those numbers to come out for you. Now, I want you going through 310 for your homework tonight. You should be able to get the rest of these done, and then we will pick up tomorrow here. Okay, so this is where we're picking up tomorrow, is calculating pH of weak acid solutions. Homework's through 310 tonight.